So we're going to work out the solutions to this lesson that was posted on D2L. It's relating to the lesson on volumes of solid with known cross-sections. First, I just want to mention that this was from Mark Sparks' daily lessons and assessment off his website. I thought it was a really good one to use, so we're just going to kind of follow his lead here and just kind of go through this task. So if I have a function f of x and g of x, and I'm interested in making cross sections and finding the volume of these cross sections, you notice that f of x is the top function, g of x is the bottom function. So when I'm creating a square, the base of that square is given here. So this follows the base of the square, and because it's a square, the height of the square is f of x minus g of x. And we want to find the area of this square. So the area would be base f of x minus g of x times the height, which is f of x minus g of x. And so therefore the area is f of x minus g of x all squared. So I mean, I could write that out in two steps if we wish. F of x minus g of x, and this simplifies to f of x minus g of x all squared. Now, when we're doing the area, this is the area of one square, and if I wanted to find the volume of that 3D solid that would be formed, I need to do the volume from where the shading starts to where it ends. So like, for example, let's say the shading goes from A to B on the x-axis, and then I do the area integral of the area of the function, or one piece, and then I do that over that entire region with respect to x. When my cross sections are isosceles right triangles, okay, so we know it's a right angle triangle, so there's a 90 degrees here. Regardless, if the area or if the cross sections being formed were isosceles right triangles, we need to find the area of one of those triangles. So the area of a triangle is 1/2 my base, which is f of x minus g of x, so that's the distance of the base, times the height, which is f of x minus g of x. And then I square, when I combine those two, I get that the area is 1/2 of f of x minus g of x squared. So again, if all cross sections were to be added up, this would create the total volume. So that total volume that we're picturing goes from A to B along the x-axis. 1/2 can be pulled outside of the integral because it has nothing to do with x. F of x minus g of x all squared, dx at the end. So you can either use these as kind of like known formulas, or you can just derive it each time, because it's really not too difficult to derive the area of one cross section. Okay, now what happens if this cross section were equilateral triangles? So we have to remember, on an equilateral triangle, the area or the angle on each of each angle is 60 degrees. So if I bisect this would be a 30-degree angle, this would be a 60-degree angle, and one of these halves, the base of one of these halves, would be f of x minus g of x cut in half, because there's two equal pieces, so 1/2 of it. So if I'm interested in finding the height of this triangle, because I need it to find the area of a triangle, I'm going to use SOHCAHTOA. So I'm going to end up using tangent. So tangent of 60 degrees is equal to opposite over adjacent, which was 1/2 f of x minus g of x. So I isolate for h. I get 1/2 tan 60 times f of x minus g of x. And then tan of 60 degrees from your unit circle would be root 3 f of x minus g of x. So that gives me an expression in the height relating to my original variables. So the area of one of these triangles would be 1/2 the base, which is f of x minus g of x, times the height, which we just got, root 3 over 2 f of x minus g of x. And then when I simplify this function up, I get root 3 over 4, and I have f of x minus g of x all squared. So if I want to do the volume of that solid that's formed, kind of a representation in blue there, over that whole interval, so I would go from A to B. My volume would have a root 3 over 4 as a constant out front. F of x minus g of x all squared dx. So that would be a representation for the volume of that solid. Now what happens if the cross section are semicircles? We need the area of a semicircle. So the area of a semicircle is, well, 1/2 of the area of a circle, so 1/2 pi r squared. So 1/2 pi, my radius is f of x minus g of x, and I square that. So if I'm interested in doing the volume of that solid that would be formed, we would add up all the cross-sectional areas, and so I would get a pi over 2, and the integral f of x minus g of x all squared. Oh, and I just made a careless error. My radius would not be f of x minus g of x. It would be f of x minus g of x divided by 2, because that was my diameter. So when I simplify this, I'd get pi over 2 times f of x minus g of x all squared divided by 4. So that would simplify to pi over 8 f of x minus g of x all squared. So this constant that comes out is pi over 8 f of x minus g of x all squared. So again, when you're doing very specific questions related to these cross-sectional volumes, you just can either use these formulas knowing that f of x represents your top function and g of x represents your bottom, or you can just kind of derive it each time you do it. So in this specific example, the region R bounded by y equals sine of pi x and a cubic function x cubed minus 4x. You can see I've labeled these functions. This one is labeled f of x because it's going to be my top function. And this is labeled g of x because it's my bottom function. And when I label top, this is, if I take this vertical kind of line, the top is the f of x and the bottom is the g of x. So that's sort of my base, f of x minus g of x. So I'm going to kind of just write that down here. Now we have to decide what is it that's being formed, kind of protruding out of the paper. So if my cross section was equilateral triangles, this equilateral triangle would be vertically standing up outside the paper. So we can either use the representation we had above, or we can just, again, derive it again, but we don't need to. So if I had equilateral triangles, I'm kind of following this volume formula that we just derived, root 3 over 4. So volume would be root 3 over 4, integral from a to b, f of x minus g of x, all squared dx. So we know my f of x, we know my g of x. According to my diagram, the shading starts at 0 and the cross section ends at 2. So my volume would be root 3 over 4, integral from 0 to 2, f of x, which is sine pi x, minus g of x, which is x cubed minus 4x. We're going to square this function and then integrate with respect to x. So you can either work this out by hand, manual we'll call it, or you can kind of do it on the calculator depending on the AP, if it's a calculator question or not. On the calculator we're going to go math number 9, which was function integral. And when you do that, I believe you should get an answer that is 4.321. Now, when the cross section is a semicircle, again, I'm taking my difference between the top and bottom, and then what would protrude out of the paper is this semicircle. This entire diameter is f of x minus g of x. So my radius would be half of that. Again, if I refer to the above with the cross sections being semicircles, I get pi over 8. So my volume would go from integral from pi over 8, or integral of pi over 8. Integral goes from 0 to 2. And then I have f of x minus g of x all squared dx. So my volume is, let's write that in black, so that purple is the known formula. So volume would be pi over 8, integral from 0 to 2. I would set up my f of x, which is sine pi x, minus my g of x, x cubed minus 4x. Square that entire thing, dx. Again, you may have to work this out manually, which you should be able to do. One part of it would be integration by substitution. The other part of it would be just kind of your versed power rule. If you're going to use the calculator, you're going to do your math number 9, which was function int. Carefully type that in, and if we've done this correctly, I believe you should get 3.918. Just remember, when you round these answers for the AP exam, you need to remember that they want it rounded to 3 decimal places, so just be careful to do that. Now, if my cross sections are isosceles right triangles, we would need to use that reference derivation that we got above, which was this top right here. It's 1/2 the integral from a to b of function f of x minus g of x. So we go 1/2 integral from a to b f of x minus g of x dx. So my volume would be 1/2. In this case, it's really clear what my a and b are. If it wasn't really clear, you may need to solve for intersection points. My f of x is sine of pi x. My g of x is x cubed minus 4x. Use a round bracket here. I square this dx. And then when you do this on your calculator or work it out manually, you should get this to work out to 4.989. If my cross sections are squares, I probably should have written this out in black because the green is the known formula. Not a big deal, I just like to color code things here. And then it works out to 4.989. Now my last formula, if the volume was a square, we would have integral from a to b, f of x minus g of x is my base. It's a square, so the height is the same thing, dx. So we work that out. Volume would be from 0 to 2. F of x is sine pi x minus g of x is x cubed minus 4x. integrate with respect to x. And again, when you do that either manually or on your calculator, you get 9.978 if you've done that correctly. Now, if the cross section are rectangles whose height is twice the length of the base, again, my base is being formed from the diagram above. So that blue section that I had highlighted like this, that represents the base, f of x minus g of x. So that's what this is, f of x minus g of x. Now we know that the height is twice the length of the base. So I'm going to draw a 2 times f of x minus g of x because it's twice as much. Now my diagram is definitely not drawn to scale here. So this one's a little bit different because even though we don't have a known formula for it, you need to be able to derive it. So my volume would be the integral from 0, or a to b in this case, just generically. My base of the rectangle is f of x minus g of x. The height of the rectangle is 2 f of x minus g of x. Now, I integrate that with respect to x because I do the integral of the area of one piece and the area of one piece and then do it over all pieces from a to b. So my volume would go from 0 to 2. The 2 can come on the outside because it's independent of x. I take my f of x, which is sine pi x. Take my g of x, which is x cubed minus 4x. Now you'll notice I have 2 of them being multiplied, so I square it, dx. And again, when you use your calculator, let's just say this was a calculator-based question, you should get 19.957. Now here we get cross sections that are rectangles whose height is 1/3 the length of the base. So here's my starting rectangle. Again, this part of my diagram represents the two-dimensional surface that's kind of shown in the diagram above with my vertical line. So this is f of x minus g of x. And then the height is 1/3 the length of the base, which is f of x minus g of x. The area is those two being multiplied together. So my volume would be the integral from a to b. The 1/3 can come on the outside. I multiply f of x minus g of x kind of twice. So it becomes squared, dx. And then when you work out this volume, 1/3, the integral goes from 0 to 2. My f of x is sine pi x. My g of x is x cubed minus 4x. I square that, integrate that with respect to x. And when you do that on your calculator, again to 3 decimal places, if this answer key is correct, this should give you 3.326. So let's continue on with some further examples. So let R be the region bounded by the graphs of y equals ln x and x minus 2 as shown below. You'll notice that there is an intersection point, there is an intersection point that represent my A and B. Find the volume of the cross section, volume formed by cross sections that are semicircles and perpendicular to the x-axis. So again, our base of that would be the f of x function minus the g of x function. Let's come write that in. So this is y equals ln x. This is my f of x because it's the function that sits above. My g of x is the linear function, which is x minus 2. This is the function that sits below. So there's f of x. There's g of x. And so there's my base. I'm going to represent that as a vertical perpendicular to the x-axis. You can see that vertical line I drew in is perpendicular. First thing we need to do is figure out the intersection points. So intersection points, we can do that using our graphing calculator. So I'm going to take ln x equate it to x minus 2, find the intersection points that we do. So when I do this, you should get x is equal to 0.15859,434, and we'll call that point A on the x-axis. And then the B point, when we do that, that will be an x coordinate. It will be 3.1461932. So we can kind of go to Desmos and just kind of quickly make sure. So you can download it as an app. Functions. So ln of x and x minus 2. So again, Desmos says 0.159 and 3.146, but again, our graphing calculators are a bit more accurate. So there's my A and B value. Now we're doing a cross section that are semicircles. So there's my base, which is ln x minus 2, which simplifies to ln x minus x plus 2. Then my cross sections are semicircles sticking out of the page. So my area of one of these is 1/2 pi. My radius is ln x minus x plus 2 divided by 2 all squared. So again, my volume of this cross section would be, now you simplify that, that's where we get the pi over 8. I'm going to substitute my A and B, which are the values coming from here and here, and I'll kind of wait till the very end to round. Now, my function is ln x minus x plus 2. We square that, dx. Now, you would need kind of integration by parts to integrate ln x, and the rest of it would be kind of reverse of power rule. So we are going to use the calculator for this because we haven't learned integration by parts. And when you use the calculator for this, you should get it to work out to 0.607. So if you have your TI, it'd be math number 9, which is function integral, and then it'll help you integrate it. What happens if the cross section is squares that are perpendicular to the x-axis? So there's my base, which is kind of represented by that vertical line I've drawn right here. So just highlight that yellow so that makes it easier to visualize. So this is ln x minus x plus 2, just like we did above. So the volume would be the area of one of those squares. Let's say I forgot my formula while we derive it. So the area of one square is ln x minus x plus 2. So the base times the height, so I square this because it's a square. And then my volume would go from A to B, which are the same numbers above that I've highlighted in yellow. F of x minus g of x, well, ln x minus x plus 2 squared is the area of one of those squares. And then we integrate over that entire region to find the volume. So when we do this, we would get this being equal to 1.545. Let's go through another example. Let f of x and g of x be the functions given by those two. They've already labeled the functions. F of x is the top, g of x is the bottom. We're interested in this area S, kind of formed between the two regions. We're interested in the volume being formed where cross sections are perpendicular to the x-axis, and the base and the cross section is a square that's protruding out of the paper. So if I draw this sort of represents my base, which is f of x minus g of x. And then we're making a square out of that. Yeah, I can draw it dotted if it helps. So the area of the square is f of x minus g of x, and then I square it. So my f of x is 1/4 sine pi x. My g of x is 4 to the negative x. And then I square it. So my volume would be, again, we would be interested in finding this intersecting point A to B. So I take the intersection between the two functions. So 1/4 plus sine pi x, make it equal to 4 to the minus x. So again, if we're on Desmos, we have 1/4 1/4 sine pi x. Now I don't know if the pi button is in here. Oh, nope, that's not the pi button. Oh, pi. Whoops, let's clean that out. So sine of pi x, 1/4 of it. And then my other function is 4 to the power of negative x. We're interested in, oh wow, I did that wrong. Let's put a plus sign between these two. And 4 to the power of negative x. So we're kind of whoops, I kind of wrote that wrong. 1 divided by 4 plus sine pi x. We're going to kind of zoom into the first quadrant, and there's that region R. So there's my first intersection point, 0.178. My second intersection point is 1. So let's kind of transfer that information here. So my A is going to be equal to 0.17 when you do it with your graphing calculator, 178.21805. My B coordinate will be a 1. So now our volume is going to be the integral from A to B, which are those A's and B's we just wrote down. F of x minus g of x squared, 1/4 sine pi x minus 4 to the minus x, all squared, integrate with respect to x. And you could do this one manually, but we're going to just do it with the calculator. So 0.250 should be that volume. Now what happens if the volume being formed is by equilateral triangles? So this is kind of the only tricky one if you don't remember the formula, because you'll have to derive the height of the function first. I'm using the base, which is f of x minus g of x, which is that dotted blue line I drew on the graph. And then once you derive that h, you're good, but we can go ahead and use the equilateral representation that we had from above, which is root 3/4 is kind of that representation. So my volume would be root 3/4, the integral from A to B, f of x minus g of x, so 1/4 plus sine pi x minus 4 to the negative x. And we integrate with respect to x. Oh, squared and integrate with respect to x. I can see I've made a slight careless error. This should be 1/4 plus. 1/4 plus. Just kind of wrote the function wrong. Well, let's write that a little better. 1/4 plus. And so when you work out this volume, so from A to B, f of x minus g of x all squared, you should get 0.108. Okay, we have kind of one more question left here before some of these practice AP questions. So we'll let f of x and g of x be defined by this function and this function on the interval 0 to 1. They've already solved our a and b for us. We're interested in this area. And then we're going to form cross-sections that are perpendicular to the x-axis. My cross-sections are going to be squares. So let's find the volume. So my volume would be the area of one square, and one square where my base is f of x minus g of x. So my function f of x is 2x, 1 minus x, minus my g of x, which is 3 bracket x minus 1 root x. I square that because the base times the height would be identical. Put my dx in there, and my volume would go from 0 to 1. So I'm integrating all those areas of the squares over 0 to 1 to get the volume. And when I do that, I get 1.493. Again, this one should be clearly possible to do by hand. I would recommend you try that by hand, and you should get an answer to work out to 1.493, just to make sure you practice your regular integral skills. Now, what happens if I'm forming semicircles that are perpendicular to the x-axis? So my base would be f of x minus g of x from the diagram. Semicircles are coming out. So my area of one of the semicircles is pi 1/2 pi r squared. My radius is f of x minus g of x. Divide by 2. Square that. So again, if you need help remembering the representations, 0 to 1. The constant out front, when I square that 2, will be pi over 8. My f of x minus g of x, so there's f of x minus g of x. Square it, dx. And again, you should be able to work this out by hand if they requested you to do that. And this would work out to 0.586. Now, what happens if the volume is being formed with equilateral triangles or right isosceles triangles? Again, we just have representations. So there's my base, f of x minus g of x. We have equilateral triangles that are protruding out of the page. So if you remember, the area of one of these was my base, which was, well, 1/2. My base is f of x minus g of x, and then my height, if you remember, was tan is 60 times the base. So root 3 times the base, which was 1/2 f of x minus g of x. So the volume would be the integral from 0 to 1. The constant out front would be root 3 over 4. And then I would do my f of x minus g of x. So 2x, 1 minus x, minus 3x minus 1 root x, all squared with respect to x. And when you work this one out, you should get 0.646. Again, you should be able to do it by hand or the calculator. And right isosceles triangle, so I have my f of x minus g of x, and then I kind of have a right isosceles triangle being formed. So my volume will be 1/2 the integral from 0 to 1, 1/2 base times height. My base and my height would be f of x minus g of x. I square it, dx. My f of x was 2x, 1 minus x, minus my g of x, which is 3x minus 1 root x, all squared, dx. And we work that out, and you get 0.746. Now again, as you're preparing for the AP exam, we can see that in Mark's lesson here, he posted a couple of AP questions. So there's a 2014 one where there's a volume, and then there's a 2010 one where there's a volume. So we can go ahead and practice these two. Now we're going to kind of pause on this because there is a section in here that we haven't covered yet. We're taking the volume of a solid generated when R is rotated about the horizontal line. We haven't actually covered that portion yet of the problems. So you may have to pause on that. Let R be the region enclosed by that function and the horizontal line 2. So if I'm looking at this section, so this section is y equals 4, and my function R is x to the 4th, or my g of x, I should say, is x to the 4th minus 2.3 x cubed plus 4. So if we can do, let's look at part B right now only. So region R is the base of a solid. So there's the base. So we're going to call that f of x minus g of x. So it'd be 4 minus x to the 4th minus 2.3 x cubed plus 4. Let's kind of clean that up. 4 minus x to the 4th plus 2.3 x cubed minus 4. The 4's cancel out, and you're left with minus x to the 4th plus 2.3 x cubed. We want the cross section to be perpendicular to the x-axis with an isosceles right triangle. So when we do this, there's a right angle, it's an isosceles right angle triangle, not an equilateral, which is what I was trying to draw. So there's my isosceles right angle triangle. So the area of one of these is 1/2 base times height. My height and base are both simplified to minus x to the 4th plus 2.3 x cubed. I square it. The volume will be the intersection point here, or well, where the shading starts. We should just kind of draw it a bit over. Shading starts, we're going to call this point A. Shading ends, we're going to call this point B. We need to find A and B using our calculator. So when you do that, A will be 0 and B will be 2.2978723. So my volume would be from 0 to A, or sorry, 0 to B, 2.2978723, 1/2, you can pull that 1/2 out if you wish, x to the 4th plus 2.3 x cubed all squared with respect to x. And when you work that out, you should be able to get 3.574. Okay. We're kind of just going to do part B right now because that's sort of where we are in this lesson. And we will also do volumes of revolution kind of next week. And again, find the area. Okay, so in this example, in the figure above, R is the shaded region. It's bounded by the horizontal line y equals 6. The vertical line x equals 2, which is this. And the function y equals 4 ln 3 minus x. So this is my region R. Okay. Find the area of R. So we've done this in areas under curves. So my area is the integral from left, where the shading starts, to where the shading ends of top curve, which is 6, minus, so if I draw this vertical slice in, my top is always my top, my bottom is always my bottom, so 6 minus 4 ln 3 minus x dx, and that would represent my area of that region R, which is 6.817 when you work it out. This one we would have to use a calculator because you don't know how to integrate ln without integration by parts. Let's look at part B. So this is our I4 outcome, which is area between curves. We've kind of talked about that last week. Find the volume of the solid generated when R is revolved about the horizontal line y equals 8. We have not covered that yet, so we're just going to call it omit for now, but kind of by the time we're done the whole volume section, you should be able to do that. And then the region R is the base of a solid, so let's draw the region R's base for one cross section. Each cross section is perpendicular to the x-axis and it's a square, so that's useful because they make it easy for us. So my square is here. I have f of x minus g of x. Find the volume of the solid. So the area of one cross section would be base f of x minus g of x. So 6 minus 4 ln 3 minus x. I square that. The volume, I would need to take the area of each square in that interval from 0 to 2, and I integrate with respect to x. So when I go ahead and do this, you should get that the volume works out to 26.267. And sorry, that's part C because we've omitted part B. Okay, we can come back and talk about both the part B's at a later, or part B on the bottom and part A and C kind of at the top later on. But we do have the ability to solve part C here. I'm going to just get you to try that for now because that relates to areas under curves.